This presentation from Fluid Maintenance Solutions focuses on filtration in high-performance machining applications. The importance of cutting fluid cleanliness in high-performance machining and grinding applications is being increasingly recognised. Typical fluid delivery systems supplied with machine tools are generally based on settlement tank principles, relying on the fine particles produced during the cutting process and the tramp oils to be retained within the sump tank. The aim of this presentation is to raise awareness of what is happening at the rear of the machine tool and the risk of contaminants remaining in the fluid, affecting what is trying to be achieved at the front of the machine and of course the overall goal of reducing cost per part. So, we're going to look at the traditional impacts on current operations, what can be expected by dealing with root cause issues, and also the benefits of this in a production environment. The United Kingdom Lubricants Association is the trade body of fluid suppliers, and this report on their behalf by PIRA generally deals with what can be done with the fluid when it comes to be disposed of. It looks at the various methods to reduce the volume and of course the cost of waste disposal. Interestingly, if you consider the reason most fluids are disposed of on average every 9 to 12 months is due to excessive contamination and smell and not necessarily due to the fluid itself reaching the end of its useful life. As regular top-ups of new fluid occur during use to compensate for evaporation or drag-out losses, this usually ensures the chemistry is kept on an even keel. Then the key question is, if we remove the contamination, then how long would the fluid last? And as machine tool performance demands increase, the traditional sump side methods of checking concentration, pH and bug growth are more aligned to health and safety aspects of fluid use. And whilst these are important, are they enough to give confidence in process control to maximise cutting performance now and in the future? There are already examples where machining emerging materials in aerospace application require production to be stopped and sumps dumped only after a few weeks of use because component surface quality defects are appearing. So, what are the root causes of these problems? At the back of the machine is a box. A conveyor may sit under the machine tool to collect the swarf and larger chips, but the finer particles, shaved off during the cutting process, fall into the sump along with the tramp oil, typically from the slideway or any hydraulic oil leaks. There is a transition phase through the fluid when this contamination enters the sump, and the particles try to settle to the bottom whilst the tramp oil floats to the surface. This settlement is impeded when pumps are running as the fluid is agitated and the contaminants disperse through the fluid volume. Sump tank designs haven't changed over recent years. You can look downstairs at the manual machines the apprentices use and the sumps will look like this. Just as the sumps during the latest 5-axis machine tools in use over in the factory of the future. Sure, high pressure and through spindle fluid delivery is the norm in CNC applications, but essentially all of the tanks retain the contaminants whether modern or manual. There is no distinction between machine tool make and whether it's a grinding, milling or turning operation. Just to demonstrate these points, we filmed apprentices here at the AMRC cleaning a sump.
So here we have a typical milling machine. At the rear of the machine, when you remove an inspection plate, you see tramp oil. This is a small sump of only a couple of 100 litres, but how likely in a production environment is there the luxury of space to completely remove the sumps like this for a thorough cleaning? Particularly the larger sumps that may hold a couple of thousands of litres of fluid in them. As the coolant continues to be sucked out, you will see how the particles have distributed around the sump, even bypassing the strainer mesh into the clean side of the sump where the coolant is delivered back to flood over the cutting tool. Using a wet vacuum to suck out the coolant and wiping out the residual contamination are common methods if you have access to all the nooks and crannies. You see how dirty the strainer mesh is, which you have seen didn't stop the contamination spreading into the clean side. The tramp oil and particles come into contact with all areas of the sump, and the only way to clean is by physical removal. Now this is interesting. You're looking at the bag filter for the 70 bar pump delivering coolant through the spindle. You can clearly see particles trapped in the bag. It looks like it's doing the job. However, this is supposed to be the clean side of the filter. You can clearly see tramp oil and particles. To give you a sense of scale, the human eyes can see about 40 microns. So, the new fill of coolant goes in and we now see the fluid delivery pumps. You can see contamination around the pump suction ports. If it's here, then it's only one step away from the cutting zone. At the end of it all, as well as the coolant to be disposed of, there is the additional hazardous waste generated and loss in potential revert value of metal.
Tramp oil is a problem on a number of different levels. These are images of clean delivery tanks from a number of machines, and you can see the tramp oil has made its way to the surface. This is where bacteria thrive, at the surface interface. Of course, you'll be familiar with the Monday morning smells when machines are turned on for the first time after the sump has settled over the weekend. Ancillary equipment is often purchased to deal with tramp oil. Skimmers in the form of disc or belt or centrifuges are often installed, which do contribute to tramp oil removal. However, there is a danger of a mindset that the problem of tramp oil is resolved. Here you can see a tramp oil separator sited at the base of the conveyor. But there is tramp oil present downstream of the separator in the high pressure delivery system. The separator is only removing the free oil already floating in its immediate vicinity. Now, let's look at particle retention. We are all familiar with curly swarf and larger chips being removed on the conveyor, but the cutting or grinding process also creates smaller particles. This independent analysis from the Mercury Centre shows the range of particle sizes up to 150 micron bypassing the filter bag and returning to the cutting zone. Cast your mind back to the video and what you saw in the clean side of the 70 bar pump filter. Filter bags are made from woven cloth, and when pressure is applied they stretch and the pores open. If you have a filter bag like the one seen in the video, nominally rated at 10 micron, then you can expect larger particles to pass through. Then there is the tramp oil. This shows over 7,000 parts per million of entrained metallics. So, what are the impacts of these contaminants remaining in the cutting fluid and returning to the cutting zone? A few questions. How dirty is the machine? How often is the inside pressure washed? Is this to remove the tramp oil deposited? Are there sticky residues coating jigs, fixtures and tooling? And are there handling hazards for operators? How long is it before the doors open, waiting for the air filter to suck the mist out? Is this because of tramp oil risk to the operator? For how long and how often are machines down because of sump dumps? And what is the cost of waste generated? Abrasive wear of pumps is common. Does your maintenance budget habitually anticipate replacement of pumps? What happens when the seals on spindles fail or automatic tool changers try to seat a taper with contamination on it? And are you sacrificing tool life earlier to overcome predicted failure? What happens when the through tool coolant holes block? These are all common occurrences and are generally accepted as normal consequences of production. However, the root cause of all these failure modes can be attributed to contamination retained within the fluid stream. Considering the health, safety and environmental risks, there is a wealth of information advising on aspects of using cutting fluids. The primary risks of breathing in mist and skin contact with the fluids is well documented. Then there is the environmental impact. The PERA report mentioned earlier indicated 400,000 tonnes of fluid are disposed of annually here in the UK. Could we expect sump life to reduce below the 9 to 12 month average in the future? With faster cutting and newer materials, we are certainly seeing sump life lower than this already in certain high performance machining applications. Then, of course, there is the disposal of consumable media, filter bags, paper rolls, and invariably the loss of metal. We can be certain waste disposal costs are going to increase in the future. So, how do we mitigate these risks and impacts, and what could be achieved by efficiently removing the particles and tramp oils out and away from the cutting fluid before it returns to the cutting zone? This is a solution for fluid delivery and swarf recovery, a proven step change in technical capability and operational reliability. The AI conveyor will recover swarf and chips to 150 micron as standard, and with the addition of a drum filter down to 50 micron. This maximises the metal recycle through traditional routes. The IFDR precision filtration solutions recover the finer particles to below 10 micron and remove tramp oil to mitigate the risk and impact of traditional filtration systems. This is an example of a total solution with integrated chiller and multiple high pressure delivery pumps for multi-spindle and turret applications, and also includes automatic fluid top-up. To put numbers against the technical capability, the IFDR uses a patented process which is free from consumable media or spare parts kit. Utilising fluid flow to remove particles, in this example for a nickel grinding application, no particles above 6 micron were evident, with 90% of those particles in the fluid stream below 1.9 micron. Of course, no mechanical device is 100% efficient, but if you improve the reliability and the efficiency of the filtration process, you will reduce the risk of particles and tramp oil remaining in the fluid stream. By taking a different approach and reconfiguring the process to extract from the cutting fluid the particles and the tramp oil before they return to the cutting zone, you will reduce the risk of traditional failure modes. Reducing tramp oil also restricts the risk of bacterial growth in the fluid. A food source is removed, and you can see that the dip slides here show no bacterial growth. These slides were from an IFDR on a grinding application. We were actually concerned these slides were a faulty batch, as no bug growth was seen over a number of weeks. So we tested the slides from the same batch in other machines using the same cutting fluid, and they registered growth. Here is a selection of improved productivity studies describing where IFDR solutions have been retrofitted to existing machine tools. The anticipated process improvement and cost reductions built the business case to replace the existing filtration systems. In this grinding application, the replacement of the OEM supplied paper media filtration system eliminated a number of continuous problems and significantly reduced operating costs on a number of different levels. The elimination of regular waste disposal was a significant cost benefit. Here, due to the dirty nature of graphite machining, the benefits of removing the particles out of the fluid stream were substantial. The removal of graphite eliminated the need for regular machine washdown, which led to a 25% increase in machine availability. And in this aluminium mill turn application, the removal of the fine aluminium particles eliminated regular high pressure pump failures and through tool coolant blockages, increasing the tool life threefold. In addition, sump life increased from weeks to 2 years, and the volume of aluminium available for recycling increased. Maximum benefit comes from specifying IFDR and AI conveyor solutions with new machine purchases, from single platform installations to large multi-platforms with centralized conveyor solutions. This demonstrates the scope and capability of IFDR solutions, a modular design which can be employed on any machine tool or grinding platform using soluble cutting fluids. And here is some background to FMS. We just wanted to touch on the TSB funding. Our patent pending SMR process was initially developed with feasibility study funding from the TSB, where we are able to divert metal-rich sludges and grinding fines from landfill or hazardous waste processing. These types of waste streams typically generate little or zero value and are often downgraded. In the case of nickel alloys, they are often blended away to make stainless steel. Following on from the funding, with our joint venture with the Fondel Group, Fondel Solutions is building a processing plant in Sheffield for advanced revert management and will be able to recycle these types of materials to or near to parent alloy status, which will significantly improve resource efficiency and value. To summarise, removing particles and tramp oil from the cutting fluid before delivering to point of use will improve productivity and quality and will minimise health, safety and environmental impacts whilst reducing maintenance interventions. Ancillary equipment like tramp oil separators may remove some of the free tramp oil, but they do not deal with the tramp oil in suspension, and this is an important aspect of fluid cleanliness. Removing bulk particles to below 10 micron has proved beneficial. And finally, please consider the fluid delivery and swarf recovery system equally as important as the machine tool itself. We hope this has sparked some interest for you. Getting the fluid delivery right is an area for quick wins, and if you would like to learn more, please do not hesitate to contact us. Thank you.